This is exam 2 part 2. First, I'll import some for the SNP because this is differential equations, so I use solve IVP to solve this solve IVP. We will plot, so we have plotly subplots import subplots. Alright. I'll input all the given information. So we have h equals 10. We have r equals 8.314. I have Cp of air equals 1000. I have Cp of water vapor equals to 2000. I have a Cp of water liquid. Okay, it's just water liquid. It's 4190. I have A equals 5. I have molar mass of air is 29 gram per meter per mole, so kilogram. And molar mass of water is 18. And we have the mass flow rate of liquid water is 0.5, and the velocity is 5, and P, the pressure is 101,325 Pascal, and we have to calculate Kc. So we have Kc equals to H over rho A. I don't have rho A up here, so let's see. Rho A equals to 1.2 H over rho A times CPA. Okay, then we will calculate the temperature of air exit. Yeah, it equals to 40 plus 234. This is the conversion from Celsius to Kelvin. Then Y exit equals to 0.9 times PV of actually, okay, no, hold on, I couldn't find that to find temperature of water in the beginning is 77 degrees Celsius, 70 degrees Celsius plus 2.15. Then we have the total height of the tower, and I want to plot like everything, all the height. So just put in space 0 and then ZN then 50. We have our gas, like the temperature of air in the beginning, like fat in the beginning, like on the top. Sorry, on the bottom, like from the bottom, we have the initial gas is it equals to the TA axis. And as I said, we have to calculate the y-axis. This equals to 0.9 times vapor pressure, like VP, like pressure of water at the temperature at the TA exit over P. So this is our Y, but we don't have I didn't like define the P, the partial pressure of water, so I have to define P like at T like this. We'll return it to 10 to the 8.07131 minus 1730.63 over 3.426 plus T minus, I have to convert, this is converting temperature back to Celsius. Right, then everything divide by, then change it to Pascal. 1325. Z is not defined. Wait, I thought, yeah, so it should, it works, but Z is it just in space of this? Why Z is not defined? Let me try to put it like it's still, oh, actually this is 0, not Z. Okay, all right, we good. Then Next, we will have our dv z and then v. We have y is v0, then temperature of water is v1, temperature of air is v2. Next is we have to calculate the mass flow rate of water gas in the in the air combination. So we have y over 1 minus y times m of water over m air times GA. Next we have G equals G plus GA plus G water. Oh, actually I have to put the GA up here. It equals to the velocity times P times MA over R times TA exit. Oh, actually I think yes. Okay. So we have GA, we have G water, the mass flow rate of air and water, and then CPA equals to CPA times GA plus CP of water, water vapor. Water vapor times G water, everything over G. Then we have M equals to like the average the molar mass, average molar mass equals to GA over G water M water plus G air over M air. And we have C water at initial at interface, concentration of water at the interface equals to PV at this is P, over R over R over temperature. Then we have this is the molar flux equals to Kc times this minus y times P pressure over R times TA. Then we have dy dz equals negative a times m over g times molar mass of water, molar flux of water. We have dt water dz. Next is water. Okay, this equal to a over L. This is water, so like L is the mass flow rate over Cp of Cp of water. No, just water. Times H times Ta minus C water minus HV times N. Okay, and for the air is similar, so it has A over G over Cp of air times H times temperature of air minus temperature of water. Alright, then we return, first is y, so like dy dz, next is dt water dz, and then dt air dz. What? It's not right. I just fixed it, so it's correct right now. And let me just put this into here. Then so z. Alright. Okay. And then I'll just put. And then I will just add this as our solution. So try to plot subplots of rows equals 3, columns equals 1, add scatter. First is the first one is y, so I say name equals y, row 1, column 1. Yep, this is the plot of y. Okay, next is add. Okay, just copy it down here as well as, but y is sol 1 and 2, name is H2O temperature, row 2 is row 3, so this is air temperature, yes, this is what we have. Mm. But like for the next, like this is just the temperature, like the air temperature gas. So we want to solve for the real air temperature. Um, for that, I will add another function up here, is a Newton function. So from skippy.integrate, I don't know, optimize import Newton. Then because of that, because I will need like another solution I'll solve here, so I'll just put it, just define it as known. Alright, then I make all of this, and everything will be inside of a function, not a function. So the function would be ta fat coverage. It would be ta. This is the real one. So this should be ta feet. A fat, okay. And we don't have anything to change. Then from here, actually like this, and then we return it as 2, and then -1 minus t. As we see here, like 2 is our temperature of air, so this is that what we need, what we want. And then at position -1, so like it is the last one right here. So yeah, like the last one is what we need to find. So like minus ta feet. All right. Let's try. Okay. And then we will find actual ta feet equals to the Newton of a feet coverage and ta feet gas. All right. Okay. Have to have global solve. Yep. Here we are. This is the part 2 of this exam.